So today we're going to be starting a new unit called probability. And so here's our first part, basic probability stuff. So let's take a look at some things that we need to know. Here are some definitions that we're going to get started for our discussion. We're going to be looking at things called an experiment is any situation in which the results are uncertain. An outcome is one of the possible results of the experiment. The sample space is a set of all possible outcomes of an experiment. An event is a subset of the sample space, and this is the set of outcomes that we are interested in. Equally likely outcomes, that means each of the outcomes has the same chance of occurring. Some example thereof would be a fair coin versus a two-headed coin. A fair coin has equally likely outcomes, a two-headed coin does not. Okay. So what is probability? If the outcomes of an experiment are equally likely, then the probability that a particular outcome will occur is the number of outcomes in the event. These are the things that we want to happen, divided by the number of outcomes in the sample space. This symbol right here just means that this is the number, it's a symbol that represents that phrase right there, and the number of the outcomes in the sample space is the probability of an event. So when we write probability of an event, we have a capital P, the parentheses, and then here is a description of the event. And you'll see some examples of this here in just a moment. So some things to remember about probability. It's kind of blurry. All right, because the number of outcomes in an event is always less than or equal to the number of outcomes in the sample space, probability is always a number between 0 and 1. It can be a fraction, it can be represented as a decimal. Sometimes they write it as a percent, but the percent, you're just going to change back to a decimal anyway. So the probability of any event occurring is always between 0 and 1. It can equal 0, it can equal 1. If it is 0, this is what's called an impossible event. That means it cannot happen. And this one over here at 1 means it definitely will happen. And then everything else is in between that. All right, so let's look at an example. You're going to flip a fair coin 2 times. Identify the following in context of the situation. I have this problem over here. We'll do it together. All right, so what would be the experiment? So what is happening? What are we doing? That's what the experiment is, and we are flipping a coin 2 times. What is our possible outcomes? Okay, what is an outcome? Okay, so what can happen when I flip a coin? Either heads or tails. So for each flip, I get either heads or tails. So what is the sample space? What is all the possible outcomes that can happen? So in this situation, this can be kind of tricky to list all these things and identify them. So part of what we're going to be learning today is how to go about doing this. And so what we want to do is we're going to look at a way to write a sample space if possible. Sometimes the number of things is just too great to write the sample space out, but we'll discuss that a little bit later. So in this situation, just look at the experiment, think about what's happening, how this will actually occur, and one possible way of doing this would be using what's called a tree diagram. A tree diagram can be used to help you identify all the outcomes in a sample space. Here's how it works. So, what can happen on our first flip? Well, I can get either a heads or a tails. After I do that, then I go to the second flip. On the second flip, well, what can happen? Well, after this flip, 2 things can happen. Or here, 2 things can happen. It's either a heads or a tails. And this one is either a heads or a tails. Those are the only things that can happen with each flip. if you follow the branches here, okay, if you follow the branches, then you end up with the full outcome in the sample space, which means I can have either a heads and a heads. So both flips were heads. The first flip was heads, the second is tails. The first was tails, the second is heads. Or they're both flips are tails. So this right here is your sample space. And so what we usually do is we usually write it as a list of items. And you can write it as, use these curly brackets to represent a set. And you just list it out, HH, HT, DH, DT, and there you go. That is your sample space. The set of all possible outcomes. And these little curly brackets mean the set of. And then also note then how many numbers are in the sample space. The number in the sample space, which is important to us, is there are 4 outcomes possible. Okay? And that's important because this number is going to be part of our probabilities. All right? So let's go back over here and take a look at what we have going on. So this is what we just did right here. So you can see that. So to find the probability of an event, we need to know the number of outcomes in an event and in the sample space. Okay? You saw up here we were able to find the number of items in a sample space. That was fairly easy. So how do we count the number of items in a set without having to count them individually like we did up here? We listed them all. We counted them individually. There are 4 of them. So we're going to learn how to do this. And so there's a lot of properties in mathematics that allow this to happen. So let's explore just a little bit more. Here's an example. How many ways can we arrange these 3 letters? Right? Let's go through this process and see if we can come up with a method for us to follow. So how many ways can I arrange those? This is the same thing as the sample space with a tree diagram. We're just going to have 3 things that can possibly happen. So let's do our tree diagram again. And the first thing that can happen is we choose a letter A, B, or C. This is our first letter. You choose a letter. Once I've made that choice, then there's only 2 things that can happen after that. If the first letter was A, I either have a B or a C. If the first letter is B, then I have A or C. And if the first letter is C, then I have A or B. That's my second letter. Well, then I have a third letter. Once I do that, I've used 2 of them already. There's only 1 choice coming off of each of these branches. And it's the letter that's not been chosen. So A, B, and C, A, C, B. This will be a C, A, B, and then A. This is your third letter. So from this, we can list our sample space. We can see how many total things are possible. So what is my sample space going to be? Let's list them all because there's not that many of them. So I have A, B, C, A, C, B. Just follow each of these branches. B, A, C, B, C, A, C, A, B, and C, B, A. So there is a total of 6 ways to arrange those letters. Okay? So looking at these 2 things that are going on here and some other stuff, we can actually come up with a rule to help us figure out counting. And then I'll show you how this all works. And that gives us the fundamental counting principle. E sub 1, E sub 2 are 2 events. The first event occurs M 1 ways. The second event occurs M 2 ways. So the number of ways the 2 events can occur is their products, M1 times M2. Okay? So let's look and expand through the same. We're going to look at the exact same example again, just from a different point of view. Okay? This is what happened in the above example with the 3 letters. the first choice, there were 3 possibilities. Now, it just means that we're going to choose 3 letters, there were 3 events. So if there's 3 events, it's going to be M1 times M2 times M3 and so forth. There's 3 letters for the first choice. There was 2 letters for the second choice, 1 letter for the third choice, and their product, 3 times 2 times 1, is 6, which is exactly how many outcomes there were in the sample space. Think about the flipping the coin. 2 things can happen in the first flip, and don't look at all these things. But in the first flip, I either get a heads or a tails. That's 2 things. In the second flip, I either get a heads or tails. That's 2 things. 2 times 2 is 4. That's why there are 4 items in the sample space. So that is what is going on here. So the question I ask now is, well, what happens if I want to arrange, instead of 3 letters, what if I wanted to arrange 4 or 5 or N? How does this pattern progress? Okay. If I wanted to do something like this with 4 letters, what's going to change? If I want to do it with 5 letters, what's going to change? If I want to do it with 1,000 letters, what's going to change? If we had 1,000 letters to look at. Well, what happens in the pattern that you see here is this pattern right here. If I have 4 objects, then it would be 4 times 3 times 2 times 1. If I have 5 objects, then it would be 5 times 4 times 3 times 2 times 1. And this mathematical multiplicational pattern has a name. It's called a factorial. It's hard to read that word, but it says factorial. Let me write it a little bit clearer. Factorial. Okay. And that is taking whatever the number is and multiplying every consecutive number down to 1. N minus 1 times n minus 2, all the way down to 3 times 2 times 1. That is called a factorial, and we designate it with the exclamation point. So this would be a number. Factorial means to take it all the way down. So this one right here would be 4 factorial. This would be 5 factorial. And when we see that symbol, we mean to do all of that. We don't have to write it all. Special note here, 0 factorial is 1, and 1 factorial is 1. And you just accept those as true. We're not going to delve into those. All right? So what's next? So what does all that mean? That has a special name. That is the ordering of a set of objects called a permutation. Permutation is an ordering, putting things in order. Okay, so if order matters, you're doing a permutation type. And there are n factorial permutations of a set of n objects, which is what factorial just means. So if I have 5 objects, then it's 5 factorial, the number of ways I can put them in order. So that would be this is the way to find a sample space without having to count them all. Because if I had 20 objects in 20 objects that I wanted to put in order, the number of ways it'd be impossible for us to list the sample space. It's impossible. And so we have to be able to count it without counting it. And so now we know if I have a group of objects, if I have however many objects I have, and I want to put them in different orders, n factorial is the way to do it because it's a permutation. So here's another example right here. How many outfits can you make if you have 3 shirts, 3 pants, and 2 pairs of shoes to choose from? Well, using our fundamental counting principle, here's how I usually do it. I have to pick a shirt. I have to pick a pants. And I have to pick a shoe. How many ways can I pick a shirt? Well, there are 3 shirts. I have 3 to choose from. How many ways can I pick a pant? Well, I have 3 pairs of pants. How many can I choose from? How many shoes do I have? Well, I have 2 pairs of shoes, so that means I have 2 to choose from. And the fundamental counting principle says that I just need to multiply those quantities together. And 3 times 3 times 2 is 18, which means I have 18 different outfits. And I don't need to list them all. Although I could do a tree diagram with it, there's no need to I know how many are going to be in the sample space, and this is the number that I need. But if I needed to write them all out, I would do a tree diagram to do so. All right, here's another example. In a math class of 25 students, how many ways can they line up at the door? So if everybody had to get up and line up, like if you were in first grade, how many ways could I line up everybody at the door? Well, this is a classic example. There's 25 people in the group. Lining somebody up at the door is an ordering. So this is an ordering of 25 people. So this is a permutation, which means the number of ways I can line up at the door is 25 factorial. Now, what would that number be on the calculator? That number would be really, 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 really long. Okay, just so you know. So that's why we don't write out the number. It literally has well over 26 numbers associated with it. So it's 26 digits. So it's pretty long. It is approximately 1.55 times 10 to the 25 power. So just tack on, move the decimal point 25 times this way, and there's literally 155 and 23 zeros. It's an extremely large number. So you can see there's no way we're going to be able to list all the different ways we can line somebody up at the door. I'm not going to try and write that many numbers in the sample space. It's too big. All right. So let's look at another example that I have. So we're going to flip a fair coin 2 times. We're back to that example again. So we had that sample space. Okay. And so how can I use this sample space? This is the list of all the possible outcomes. So now we're going to look at a probability. What is the probability of flipping 2 tails? That means, and you can write it this way too, probability of a tails and a tails. Well, the definition of probability is the number of favorable outcomes, so the number of things where this occur, and over the number of things that can occur in the sample space. Well, I know the sample space was 4. So in our sample space, how many of these things are tails? There's only 1. So the probability of flipping 2 tails is 1/4. Then you would just leave it like that. So what is the probability of flipping a heads and tails? Okay. 1 heads, 1 tails, not in any particular order. Okay. As long as there's a heads and a tails involved, well, that happens here and here. So that is 2 times out of the 4, and then that has to be reduced to 1/2. So remember, in all your fractions, they must be reduced to the lowest terms. Don't change the decimals, please, okay? Because it's an approximation, unless it happens exactly. Here's another example. The experiment is we're going to flip a fair coin 3 times. Well, based off of our fundamental counting principles, I already know how many numbers are in the sample space. If I flip a coin once, there's 2 things that can happen. If I flip it twice, there's 2 things that can happen. If I flip it a 3rd time, there's 2 things that can happen. So there should be 8 numbers in our sample space. So find the sample space. That means we want to list it. This one we can actually do because it's not too big. It's only 8 items. Heads and tails. Each of these branch off to a heads and tails. And then each of those branch off to a heads and tail. And then follow each branch and you can write out your sample space. HHH, HTH. Oh, I missed it. HHT for the second line. HHH, HHT, HTH, HTT. And then this one, D, and then DHT, and then EDH, and EDT. That is my sample space, and those are my 8 items. What is the probability that I will get 2 heads and 1 tail? Probability of 2 heads and 1 tail. Well, we look over here. 2 heads and 1 tail. That's 1. That's 2. That's 3. That's it. I have 3 out of 8. What's the probability that I have all heads? There's only one of those out of the 8. And that's how probability works. Okay? And so once you have your understanding of your sample space or how many items are in it, you want to find out how many ways this outcome occurs. Okay? Your favorable outcomes means 2 heads and 1 tail. I'm looking for that. How many times does that occur? And that is how you determine your probability. There'll be more examples in class, and that is our first lesson for probability.